So bad. It's similar to my homeworks. I feel like the last one is example stuff, but it's starting to yeah.
Y'all love pizza? This is what my life looks like these days. It's awfully nice. How are y'all doing? All right, we have a medium-sized one to do today. We are. This may feel a bit in the weeds, but this is one of the big ideas for. Do y'all send those like crash reports? I never do. This is one of the big ones for evaluating whether our model is actually sort of in the right ballpark. We're going to talk about a couple of model assumptions that we take into our statistical models, not just for the small general linear models that we've been building so far, but also when we start building more complex ones, these are some of the tools we need, not to build them, but to check whether they've run correctly. So that's where we're going today. We're going to talk about model diagnostics, which maybe isn't something you woke up this morning hoping to think about. Love the honesty. But this is one of those things any proficient economic data analyst will need to think about these things. This is one of those things I will look for on the final project. So it's really just evaluating how good the model is that you built. Okay, so that's where we're going. Sorry, I haven't posted the homework for like 4.1 and 4.2 yet. That's on me. I'm going to give you plenty of time to do it. I've just gotten a day or so behind on my work. So I'll get that to you as soon as I can. Let's see, any other housekeeping? All right, y'all hanging in there? Yeah, Mairead. Nice, yeah. I think I've returned project 2 grades to you. If I haven't, just let me know. There is no project 3. We're gonna skip just directly to project 4, which will just be an extension of the tools we're building. But that will happen after we take mini exam 4. All right. So in the off chance I decide not to post 4 homeworks for part 4, would you be excited about that? I think I'll post all of them, but maybe not make them all required, just so you can get some practice if you want that. But I think at this point it's going to be, because I haven't posted them yet, I think it'll be a lot of work to do in the next week or so. All right, so that's where we're going. Y'all want to talk about model assumptions? There's this new pizza place in Bloomfield, which is very good. I don't remember the name, but it's right beside Constellation Coffee, if you know where that is. The pizza is very good. Max agrees. They also have like a cheesesteak, which is like, it's one of the best ones I've had outside of Philly. I would never compare it to a cheesesteak from Philly directly, but it's very good. They even use, anyone from Philly? What's the name of the cheese that's used in the cheesesteak?
Sharp.
Yeah. So they use that one, which I've never had that outside of Philly, and I would never be able to pronounce it because I'm not from Philly. Say it again. Cooper Sharp. Yeah. Or Coop Sharp. Yeah, good stuff. So yeah, their cheesesteaks use Cooper Sharp. Okay, enough cute pictures. What if we just looked at pictures for a semester? think the university would not be happy with me. Okay, so we're going to talk about model diagnostics. This may feel a bit in the weeds, but there are good reasons for doing this, which we're going to talk about next class with time series models. A lot of you are going to feel inspired to build a time series statistical model, and next class, I hope, will convince you otherwise. So to think about whether our models are correct, we're going to talk about 4 model assumptions today. So what we've done so far with building statistical models, we built this entire apparatus of sampling error using the central limit theorem, and then building levels of confidence, which allowed us to make claims about our sample relative to any null hypothesis we wished. This is all from part 3.4. In part 4.1, we started introducing our first predictor variables. So this we talked through the sampling distribution of the sample slopes. So if we have a bit of data, we build a statistical model minimizing the mean squared error, giving us a slope. Every time we redraw the sample, we get a distribution of sample slopes. We can use the same ideas we built in part 3, but applied to sample slopes to make claims about a null hypothesis. So our default null in general is going to be that there is no relationship between the variables. And then we can just make statistical claims about the probability of seeing the data, the sample slope that we do, given our null hypothesis. And this gives us our p-value. When we have small p-values, we say our data is very inconsistent with our null hypothesis. This is our hypothesis testing approach. And just to remind you, we haven't and probably won't talk about rejection regions in this class. It's not required for any of what we do. All we need are p-values. So the probability of seeing our sample given our null hypothesis. And then last class we built a simple extension of our bivariate numerical predictor example. Instead of using a numerical variable to predict another numerical variable, we said, what if we encode a binary predictor variable as ones and zeros and used that as a predictor? That allowed us to set up a model that looked like this, where we have 2 categories on the horizontal axis, no and yes, and then we just said, let's use ones and zeros to predict the vertical axis values for the 2 different groups. And this allowed us to use the same apparatus we constructed in part 4.1, but applied to binary categorical variables. So we could check whether there were differences in means between these 2 groups. And if you remember from your stats class, this is the same kind of test as what you used with the 2-sample t-test, just checking whether the 2 groups are different. It's just, we can do it in a more general setting, which is part of what's incredibly powerful about this approach. It's like, we can do all types of tests using one umbrella technique. All right, so this is what we did last class. We said we can just check whether these 2 are different. The beta, so the beta 1, tells us the slope, the difference between the 2 groups. And then we can just check whether that's statistically different from 0, giving us a p-value, and then we can make probabilistic claims about the difference. So that's what we did last time. But every time we run this, whatever the model is, one of these 3 or one of the ones we're going to build in part 5, each one of these produces, our coefficients, so our estimates of betas, our standard errors, so the sampling variation given to us by the central limit theorem, and p-values. But sometimes, as I'm going to show you, a linear model isn't necessarily the right tool for the job. So I'm going to show you a couple of examples of where linear models aren't appropriate, just straight out of the box. and we have to think a little more carefully about how we apply our general linear model in those contexts. We're going to be able to handle a lot of troubling details with the general linear model, but we have to think about whether our model is appropriate. So let me show you two figures here. I have model 1 and model 2. These are obviously different data sets. If you're just looking at these, which model do you think offers better predictions? This may feel like if this feels like an easy question, maybe try to tell me why. But think through which one of these models offers better predictions, like which of the models is better, and think about why that is the case. Let's take like a minute here. Say hello to the people around you. Tell them they're doing great. If they're taking intermediate micro mini exams today, tell them they did great or they will do great. And then figure out which one of these two models is better. So model 1 or model 2. Take about a minute. All right. If you're still chatting about this, that's great. There are a lot of nuances here. How many of you think model 1 makes the better prediction? Okay, someone tell me why. Pete.
There's an even amount of data. Well, I should put there's an even amount of data on both sides of the line for both of them.
Yeah.
But it looks like it's more evenly spread out. Whereas
Okay.
model 2 looks like there's more data above the line at the beginning and the end.
Yeah.
And sort of on the line in the middle, while model 1 kind of has everything scattered throughout.
Yeah. So nice. So this is, I think, a really nice answer. We're saying model 1 maybe offers a better fit because the sort of spread around the model itself is very even no matter where we are on the horizontal axis. For model 2, if we look at small predictor variable values, most of the data is actually above the model. In the middle, most of the data is below the model, and then for large values, most of the data is above the model. So the predicted value, even though the data points are evenly split above and below in both of these cases, there's sort of systematic error in the second model. Anyone thought that's not a complete sentence. Did anyone think the second model was the better statistical model? Yeah, Claire.
I mean, after hearing their explanation, mine's kind of the opposite.
Okay.
Like I thought, yes, there are especially in the top, there's 4 outliers, but I just feel more condensed. I would assume there's less variation in error.
Oh yeah.
So I just thought maybe it would be a little more close best out of fit, but I don't know.
Yeah, nice. So this is an interesting observation. What Claire's saying is, in the first model, the data points are sort of more spread out. Like there's more just the way we visualized it at least, there's more variability around the model than in the second one. So the second one is like, it looks kind of more tightly clustered around the model potentially. So we're actually going to get into this. The part of the correct answer is actually Pete's. So I'm going to give you 10 lecture points for answering a question incorrectly. I love it. The part of the reason that the first model is the better predictor is because no matter where you are on the horizontal axis, the model prediction falls squarely in the middle of the data. If we look at a very high horizontal value for model 1, like equal data is on both sides, roughly, right? It's pretty close. But for model 2, all of the data is above the line. So we're systematically underestimating the expected value for large predicted values. So we plug in an x with a very high value, we're going to underestimate the prediction. Yeah, Claire.
So like, would you just, for model 2, obviously they're different data, so like, would this just not be a good like representation of model 4? Because like, how would you make a linear line when like it's really kind of curved?
Yeah, great question. Should we talk about it? I've developed an entire lecture to answer this question.
Okay.
Yeah, it's very nice. I mean, in some ways. We're going to come back to like how we address this problem. The short answer is we'd have to transform one of the variables. So sometimes this looks like it could be exponential. So we'd have to think about maybe taking a log of one of the variables. Yeah. Great question. What else? You don't get points for that second question. So that's good. Okay, so this is the way to think about whether our assumptions are being modeled correctly. Are there systematic errors in the way we're making predictions? Are there differences across predicted values? And we're going to develop a systematic approach for thinking about these things. Okay, so the first assumption we need when we're constructing statistical models. Remember the central limit theorem? It requires a couple of things. It's close to magic, but it's not actually magic. We have a few assumptions. The first one is linearity. So this is the assumption we violated in model 2 in the previous slide. The underlying relationship is actually not linear. So we need to think carefully about our use of the general linear model when we're using data with nonlinear underlying relationships. The second one is this fancy word. Every semester, people get tripped up pronouncing this. This is HOMO, so the same, skedasticity, which is like variability. So this is homoskedasticity. It's if you can't pronounce it, you're in great company. This just means we need there to be the same variability in the data across all predictor values. I'm going to show you a picture of what this looks like. It's a scary word. It's not a scary concept. The third one is independence. We just need each observation to be independent, so like unrelated to the one that came before it. If you're thinking about time series data, this is the one that should be concerning to you. We need individual values to be unrelated to the one that came before it. And then the last one is normality. We just need the error terms, so the residual, to be unrelated or to follow a normal distribution. This is the one that matters the least. We're going to talk through all 4 of these, and I'm going to give you some code to be able to check them. I require you to work with these in your final project. This will be one of the things I check for in my rubric. Okay, so why do we need to? Well, I think the motivating picture, Model 1 and Model 2, I think gives you a somewhat good example for why we need to check. our predictions are just going to be wrong. We can also bias our estimates. So the estimates themselves may not be centered on 0. The standard errors are definitely going to be wrong. So the variability can be wrong if we mess up the standard error. And then if our standard errors aren't correct, then our p-values are definitely not correct, right? The standard error constructs the normal distribution centered on our null hypothesis, and if that spread isn't correct, then our p-values, the area in the tails more extreme than our sample, are also going to be incorrect. And the p-value is part of how we evaluate the consistency of our null hypothesis with our data. So that's a pretty big deal, right? If our p-values are wrong systematically, this presents real problems for inference broadly in science. And then I think this is the easiest thing to see, that the predictions aren't reliable. So we're going to use two things. We're going to use the residuals. I'm going to show you a figure of what these things look like. We're going to use the residuals, sort of the mismatch between the data and the model, as well as the predicted values given to us by the model. We're going to use those two things to systematically evaluate whether our models are correct. We're going to do this in 3 different ways across 4 different assumptions. So that's where we're going. We call a model specified if it's modeling the data correctly. That's just one of the sort of terms of art. Are there any questions before we jump in? Or have we already jumped? Maybe we already have. So these are 2 pictures. We're going to use these 2 components of our model to evaluate the model fit. The first one is the model residual. You've seen pictures of this before. This is just, we fit a model. We're going to take the difference between the model and the data, which is our residual, which tells us essentially how far off the model is. So the error of our model. And then the second thing we're going to do is get the estimates. So I'm going to plug in each one of our data values, so our x value in our data, and then I'm going to get a prediction at each one of those x values from our data set. And that's going to give us our estimates. This looks really clean and linear, and that's because our statistical model is linear. So it makes a lot of sense. Okay, any questions here? So I'm going to ask you to do this by hand. Just kidding. We have a computer. I will never ask you to do this by hand. So what we're going to do is actually go through and calculate residuals for the data set we used last time. We had happiness and GDP, comparing whether higher GDP per capita countries are happier. Do you remember this from exercise 4.2? We didn't actually submit exercise 4.2. We're going to submit a similar figure today. All right. You want to take bets on whether the notebook works? Yeah. Oh, yeah. Yes, it works. Yeah. I'm going to take a bet that this works because I checked it right before class. Although I've done that before and it hasn't worked in some cases. So here's our exercise. We're going to walk through and actually calculate some residuals. So we're going to spend a second just getting familiar with this. What I want you to do is construct a general linear model predicting log GDP using, predicting life evaluation using log GDP per capita. So I'm going to take the training wheels off here a little bit. I want you to actually construct this model. You're going to do it from scratch. I don't have this code in the slides. You can reference the skills we've used before. We did this last class, so you can reference some of the material we did last class. But I want you to get a sense of like getting started with this without me telling you exactly what to do. So build the statistical model predicting life evaluation using log GDP per capita. It will take maybe 3 to 4 minutes to do this. If you get stuck, reach out to someone next to you, or just chat about it the whole way. You don't have to get stuck. Be good to your neighbors. It's a good practice in life. And you can talk to each other. At least I think you can. Okay, how many people have a result? Okay, if you don't have a result, maybe check with someone next to you. This is a good chance to, I hope you're feeling the, like, I can show you how to do it, but I also want you to feel what it's like to not know. So check with someone next to you if you haven't been able to run this yet. Okay, if you're still working, that's great. Feel free to keep chatting. I've been writing these kinds of models all of my adult life. I'm going to show you how I do it and some of the mistakes I make systematically. And then you can check your work against mine. So when I'm constructing this, I want to first just reference the package I'm going to use. So in this case, it's stats models formulas, which we've loaded above. So SMF is our main tool. So this is SMF. And then I went OLS. And then I'm just going to write in the statistical model. So this is, I went life evaluation squiggly. And then I went log GDP per capita. And then I just need to specify the data set. So data is equal to data. If I run this on its own, oh, it's saying stats models has no OLS. So if I run into an error like this, I need to think about like how to fix it, right? So that it's giving me an error, and I need to think about how to solve this error. One thing I could do is just so SMF, and then just see what's available. So it looks like I just used a capital OLS instead of a lowercase. So if I run into this error, like personally, I don't know exactly how to solve it. So then I'm just going to use the tools available to me to go about solving it. If you're running into these kinds of errors, everyone does. Even the best coders will run into these errors. You don't have to be perfect with these things. OLS, and then I'll run this. So the second error I found is life evaluation is not defined. This is probably just because I misspelled it. So I'm just going to go up and copy the title, and that turns out to be true. Nice. So now I have the model fitted, or I have the model defined, but I need to fit it. So I'm just going to write fit, and then if I run this, it's fitted the model, but it doesn't tell me anything. So I'm just going to write summary on the end. And this is going to print out the model results. Okay, so this is nice. If I print this out using print, I can see this a little bit nicer. But what I actually want is, I want model. I'm going to define the model just directly. And then we have some code in the slides to get residuals. So I'm going to talk you through what we're doing here. We've run through and we've fit the model. We can print out summaries if we like. So we did this in one line before, but we can do it in two. So model.summary, and this would just print out the summary directly. But what I want for our purpose today is to plot the residuals. So I'm just going to get the residuals and the prediction. So we've defined model, which is our fitted model. And from the fitted model, we can get a lot of things like the summary, but we can also get residuals. So I'm going to say model.residuals. So here again, I have to figure out how I get the residuals. And in this case, it's, again, a spelling error. So it's just resid. For some reason, when people write code, they like to abbreviate things. But then it makes it harder to find. So here we have the model residuals. This is just a list of all of the mistakes the model is making. I'm going to define this as residuals. And then the second thing I'm going to do is actually go through and make predictions. So this is model.predict. So the dot operator, like we've talked about, is just running a sub package. So I'm just getting from model, I'm getting the predictions. And here I'm just going to make predictions over all of the data points. We did this in class using an actual equation. So remember we wrote out the equation for a line and then plugged in some x values. Here we're just going to do this for all of the x values in our data set. So we're making predictions using the data points. Okay, so nice. The last thing we're going to do is actually create a residual plot. And the way we do this is by plotting on the horizontal axis the predictions, and then on the vertical axis the residuals. So if I write this out, this is sns.scatter plot. This is residuals, sorry, predictions is our x value, and then residuals is our y value. My internal spell check is never turned on. We need PLT. So one thing you should learn is to not follow my live coding and just follow the code from the slides. My third self-deprecating joke you haven't laughed at today. Fourth self-deprecating joke is that they're not even funny. It's actually probably true. Okay, some of you laughed. You know what, I have a PhD in economics, not stand-up. That's not self-deprecating. So here we have our scatter plot of residuals. The horizontal axis, I have the predicted values. So this is a bunch of predictions. And then on the vertical axis, I have the residuals. And what this does is gives us a systematic perspective on where the model is making mistakes. And so what we want to see is that the model isn't making large systematic mistakes at any particular horizontal value. So at a predicted value, is our error going to be systematically off? One thing we could do is add a horizontal line. And what we'd like to see is for it to be evenly spread out around this horizontal line. Okay, so this is the core tool we're going to use the rest of class. This is what we call a residual plot. This is how we evaluate whether our model is working correctly. All right, any questions here? Do you enjoy seeing me make mistakes? No? One of the things I'm not sure I communicated to you effectively at the beginning of the semester is when you're writing code, you're going to make a lot of mistakes. I've been writing Python since I was like 22, and I still make plenty of mistakes every day, as you can see, as I'm doing this live. Okay, so nice. So this is our residual plot. If you don't like watching me make mistakes, maybe take another class. Wow, that's harsh. I'm glad you're here. Okay, so I'm going to show you two figures here. These are residual plots. I have model 1 and I have model 2. And these are just exactly what we just did, right? These are figures showing the relationship between our predicted value on the horizontal axis and then our residual on the vertical axis. This is a question for you. Which one of these two models, model 1 or model 2, appears to violate the linearity assumption? Say a number to your neighbor. I know a lot of you have answers. Give a number and then I'll ask for your answers. Model 1 violates the linearity assumption. Anyone wish to disagree with me? Yeah.
What are the assumptions that it should be in a straight line?
Yeah, so we would want our errors to not be in one direction systematically. So yes, I'm wrong. Yeah, so the correct answer here is 2. And the reason we can see that it's 2, model 1 looks actually really nice, right? We have errors distributed very nicely on either side, no matter where we are at the fitted value. Model 2, we can see there are systematic errors. So just like in our motivating example for today, we make lots of errors, all in the same direction for small values. For medium-sized values, we're making errors systematically in the other direction, so we're over-predicting. And then for large values, we're under-predicting again. One of the things the residual plot allows us to do is see these kinds of things. We could just look at the figure itself, the relationship between the two variables. In 2 dimensions, this works, but when we start talking about more than 2 dimensions in part 5, we can't actually visualize the error. So we need a residual plot to be able to do that. All right, so this is the picture. You can see the model 1 is essentially equally wrong at any predicted value, and model 2 has larger errors at the extremes. Okay, and in the middle. Any questions here? So when you run your statistical model, the first thing to do is check whether it's being run correctly. The residual plot will give you a picture of that really nicely. This is just an example of nonlinearity. So here, on the horizontal axis, I have age. The vertical axis, I have annual income. The older you get, the more money you make in general. But this is not a linear relationship. When you sort of hit the peak of your career, you kind of level off in terms of income. So you can see this upward relationship, which is positive news for you. And then later in life, you'll continue to make more the older you get as you gain work experience and such. But the slope becomes flatter. The true relationship is in green. So I constructed this data to match an empirical reality, so I know exactly what the true relationship is. And I fitted it with a linear relationship. So this is just, I'm predicting annual income using age. And on the side here, I have the residual plot for that model. And what you can see is we have systematic error in the middle and at both extremes. This is the true relationship for the residuals. And what you can see is the nonlinearity in the original data ends up giving us nonlinearity in the residual plot, exactly as you'd expect. We're essentially just taking the original data and then flattening it out to give us the residual plot. That's essentially what the residuals are doing. I'm just going to take this and then slide it over and make the slope flat. Okay, any questions here? So if you're using, if you're thinking about nonlinear relationships like this, there are a couple of things we can do. We're going to talk about adding control variables in part 5. One thing you can do is just add more terms. So instead of fitting a linear relationship, you can fit a polynomial. So here, if we're trying to predict income using age, we could actually just add a second predictor variable, age squared. And this would give us some curvature to the model. So we can do that. The other thing we could do is use a logarithm. So a log transform of the x or y variables, which is something we've done quite a bit in this class. All right, any questions here? So this is a common problem you'll run into. In fact, I think last semester, at least a third of the final projects had some nonlinearity in them. So this is something you'll run into a lot. And these are some of the approaches for handling them. Okay, second assumption, heteroscedasticity or homoscedasticity. So question for you. Tell your neighbor which model shows homoscedasticity. And then I'll ask you for an answer. Okay, someone help me out here. I'm going to claim the answer is model 1. Someone want to disagree with me? It's a very confrontational way of posing this question. How many of you think model 1 shows homoscedasticity? How many of you think model 2 shows homoscedasticity? Okay, nice. Model 1 has equal variance everywhere on the horizontal axis. This is what we're looking for. This is very nice. It's not perfect as you can see. Every time we run we draw data from the population distribution, the data is going to be the same, sampling error. So it's never going to be exactly perfectly homoscedastic. But this looks pretty good. This one shows a real problem. Let me just highlight the error terms. So here you can see there are small error terms for small x values, and then there are large error terms for large x values. Sometimes it goes the other direction, where we have large error terms for small x values and small error terms for large x values. The main point here is that the error terms are not uniformly distributed. They vary. They systematically vary against the horizontal axis. This is a problem. We construct our p-values using the distribution of error terms. We need the model to have like standard errors that are consistent everywhere. So this is any questions about this? This is another example. So this is the horizontal axis. I have years of education, which we are actually going to use from the census records. We're going to look at years of education and an annual wage using like real observations at the beginning of part 5. But this is just some simulated data to show you an empirical regularity that we see in the data. This on the vertical axis, this is annual wages. The horizontal axis is years of education. The more educated you are, the higher your wage is overall, on average. And so we can predict annual wage using years of education. But one thing you'll notice is that the more education you have, the more variable your income. So even though on average you have higher income with higher education, there's more variability among the higher educated. And so when we plot just the residual plots, one thing we see is that the income for higher predicted values is actually much larger. So the lower predicted values have lower standard errors than do higher predicted values. And this is a problem as you might intuitively expect. The standard error is what we use to construct the sampling distribution, which we then use to construct our p-values. And if our standard error depends where we are on the distribution, this leads to uninformative p-values. Our p-values will be systematically wrong. So we can fix this. And it turns out there's actually a really nice bit of code that can fix this. What we use is what we call robust standard errors. So all we do is we just essentially tell the computer to account for this problem. And then we can just adjust the standard errors to account for heteroscedasticity. And all we do is we just add this little thing inside the fit. So we just need the covariance type to be heteroscedastic consistent. Okay, any questions here? The way this is actually done is beyond the scope of this class. This is one of those rare times where I'm going to tell you to use this. This just essentially allows us to account for varying standard errors. Okay, nice. The last two assumptions, this one is what we call independence. So let me talk you through what I'm showing here. This is the one we're going to return to next class. This is a lagged residual plot. So on the horizontal axis, I have the residual for the previous prediction. So we just have a list of data. All I'm going to do is take the prediction I made in the previous row and then compare that to the model prediction in the next row. What I need is that the error terms between rows are unrelated to each other. So if I take repeated observations, I just need that the error terms are not related to each other, one after the other. So if I'm claiming that assumption, that I need independence, which one of these lagged residual plots shows independence? Horizontal axis, I have the residual from the previous period, and the vertical axis, I have the current residual. Which one of these shows independence? Tell your neighbor, and then I'll ask you. I get them too. Okay. How many of you think Model 1 satisfies independence? Hands up. Be proud. How about, how many of you think Model 2 satisfies independence? Yeah, be proud about your answers. Is that a hand? Nice. So all four of you get lecture points. The answer is 1. Someone who said 1, want to tell me why it's 1 and not 2? Yeah.
I just thought it looks like Y isn't really influenced by X. It doesn't follow any kind of pattern.
Yeah. So essentially, we're saying we can't predict the next residual using the previous one. There's no real pattern between them. Another way of thinking about this is that the error terms are independent of what came before them, which is the independence assumption. Yeah, very nice. I'm sorry, remind me of your name.
Anthony.
Anthony. You've told me your name so many times and I keep forgetting for some reason. I appreciate it. Okay. Anyone want to add to what Anthony said? Any intuitive way of seeing the independence assumption in flagged residuals? We just really need there to not be any relationship between the residual and what came before it. This is a real problem, as you might expect, when we deal with time series data, because fundamentally, each point is related to what came before it. So we're going to talk about this next class. We're going to build a statistical model for time series. I'm going to show you some tools to handle some of these problems. And then I'm going to tell you generally to not do time series. Okay, so I'm just going to draw a line through the data. This is essentially what Anthony was sort of trying to communicate, was if we draw a line through the data, we kind of need it to be flat. The second model is definitely not flat. There's a positive relationship, which tells us that the residuals are correlated one to the next. And that's a violation of the independence assumption. We call this autocorrelation if they're correlated in time, and we're going to spend a lot of time talking about this. Okay, so this is just some code. We're going to check this in our slides. Nope, in our notebook. I can't write perfect code. My self-deprecating jokes don't land. I make mistakes in the slides. I don't even know what a notebook is called. You forgive me? Oh, that's really nice. I appreciate it. Okay, so we're going to set up a lagged residual plot. So we've constructed our residuals. I'm just going to, the first thing I'm going to do is, let's just write out residuals. This is just a list of residuals. This is just, row 0, here's the error I made. Row 13, here's the error I made, and so on. What I want is to get the lagged version. So I want not the first one, but I want everything after the first one. So I'm going to start at the first row. So I'm dropping the first row, and I'm going to pick up with the second row and just take everything else. So I've shifted everything down by 1. I've just removed the first one. And then the second thing I'm going to do is, so let's call this, we're just going to plot this against residuals. But I want everything but the last row. So this is going to be everything up until the last row. And this is just Python syntax. You don't need to know this. But this is everything up to the last row. So this is 1956. And then we need everything up into the last row, which will give us not the last row. And then we're just going to plot this against itself. So we'll do, let's say, plt.scatter. Weirdly, we're not using Seaborn here. And we'll just plot one against the next. This gives us our residual plot, or lagged residual plot. Okay. So we're going to come back and evaluate the assumptions for our model that we built with GDP and life satisfaction. But I want to talk about this last assumption, normality of residuals, before we do that. So the last assumption is that the residuals themselves are distributed normally. So we need our residuals themselves to follow a normal distribution. This is technically required, but in practice, partly due to the magic of the central limit theorem, this is actually not strictly required. In general, if your sample size is large enough, you can actually drop this. So this is one of the least important assumptions, which is why I put it at the end. The central limit theorem actually tells us that we don't need to know the underlying distribution of our error terms, just like we don't need to know the underlying distribution of the population to be able to make claims about the sampling variation. Right? The central limit theorem just tells us it's going to be approximately normal. So here, even though we mention this, in practice, this is not strictly required. But we can test it. So we're going to hop over to the notebook and then just plot out the distribution of residuals. So let's do sns.hist plot and then residuals. Okay. Any questions here? Does this look normal? I see one no, I see one maybe, I see a bunch of yeses. I think this is pretty close. It's like pretty closely centered on 0. I would not say this is like a very nice normal shape, but it has some of the characteristics of a normal distribution. Turns out this one isn't so important. So let's go back to the first two assumptions, assumption 1 and assumption 2. What we did at the beginning is plot the residual plot. We have the prediction on the horizontal axis, and we have the residual on the vertical axis. What do you all think? Turn to your neighbor, try to evaluate assumptions 1 and 2. This is linearity and homoscedasticity. And we can evaluate both of those model assumptions using the residual plot. Discuss this with your neighbor, whether you think the model we built last class satisfies those first two assumptions. What do you all think? What about model assumption 1, linearity? How many of you, raise your hand if you think this satisfies linearity. Raise your hand if you think this does not satisfy linearity. Okay, most people abstained from answering the question. I see you. Someone want to make the case for this being linear? No one. All right. Maybe I will. Oh, Marie.
I was gonna say most of the data is like a general spread of our residual line, and also the data earlier we saw it had pretty good.
Nice. So yeah, some of you would have plotted the relationship above, and I mean we did this last class too, and the relationship between these variables looks very linear. One way you can check, you could just look at it and see that it's linear. You could also sort of systematically go through. So there's about the same number of data points, errors above the line as there are below at every point on the horizontal axis. Okay, what about homoscedasticity? I mean, I generally agree that this looks linear to me. What about homoscedasticity? Have you already talked about this? Yeah.
I'd argue it's there's not homoscedasticity. Just because at the end, it seems like the tail end, it starts to kind of converge a little bit more.
Yeah, so sort of like a cone shape. Yeah. Matt, right? Matt's saying, look, this looks what we call heteroscedastic. It's not homoscedastic. So the variability varies. So maybe less variation in the upper values and more variation in the smaller values. Anyone disagree with this? When I look at this, I sort of see something similar. There's not a clear test for these things. But if I were seeing this, I would probably include heteroscedastic robust standard errors, like we talked about in the slides. Do y'all know generally why this might be? I mean, think about what we're doing. We're trying to predict happiness using GDP per capita. So what we're saying is there's more variability in happiness between countries that are poor. Very wealthy countries all have about the same level of happiness. So lots of these countries have about the same level of happiness. But there's more variation in the happiness scores of poorer countries. That's what this is telling us. This is empirical data. Like, this is coming from the real world. This is a fact that you've seen come directly from a data set. Okay, any questions? I love questions, so when you say no, I get a little sad. Just kidding. There can be no questions. Okay, so assumption 3. Take a look at this. Have you all thought about this one yet? Let's spend like a minute thinking about whether the lagged residual plot shows us independence. Does this look like independent data? Yeah. What do you all think? Do we satisfy independence? Hands up for yes. Hands up for no. Same 3 contrarians. Okay, so I will ask you for your answers. Someone who answered yes, that this satisfies independence. Someone want to represent that perspective? Like, what do you see in this that tells you independence? Yeah.
You can't really tell where the next point's going to be.
Okay. Yeah, so
No correlation.
yeah, it doesn't look like there's a lot of correlation here. If you were to draw a line of best fit through this, which way would it go? Would it be sloped downward or sloped upward? It could go either way. Yeah, very nice. One of the contrarians want to tell me?
I just think it's like pretty centered up into the it was reasonably with like they're
Oh yeah.
like,
Yep.
be pretty confident that like not like opposite axes. Like
Yeah.
0 and
So 0 and 0. So you're saying it's
it would probably be
pretty close to 0. So you're seeing that it's up into the right, giving like indicating that that there might be a relationship between these variables. Okay. Any other perspectives here? To me, that indicates that it's independent. That there doesn't seem to be much of a relationship here. When I look at this. Centered on 0, and it doesn't look like there's a clear pattern to me. 10 lecture points. Appreciate the perspective. We can disagree about these things, so maybe I shouldn't give lecture points for this. To me, this looks generally pretty independent, but if you see some autocorrelation, that might not be wrong either. Okay, any questions here? If you wanted to test this, you would just fit a statistical model to it. You could predict the lagged residual using the previous one. All right, so great. The last one is normality of residuals, and we've already sort of talked about this. I think this is definitely not a normal distribution, but it has some of the characteristics of a normal distribution. But it turns out, given our sample size of like over 100, we don't particularly need this as one of our assumptions, which is very nice news. All right, so I will require this. This is one of the core diagnostics of our models. It feels a bit in the weeds, but the reason we do this is because we can run the general linear model in inappropriate contexts. And these diagnostics will tell us whether our model is doing what we claim it to. So this is sort of appropriate use of the general linear model. Okay, any questions? Upload your residual plot to Gradescope, and then I will see you all on Thursday. If you're taking an exam today, good luck. You'll do great.